I will talk today about a very interesting problem, namely, can we apply machine learning methods to analyze Lustre log data to make predictions in the future when LBUG occur, and can we somehow understand the LBUG? So that's my talk. So here's a brief overview. I will talk just briefly LBUGs in Lustre and the implications and how this Lustre log data is processed. I briefly introduce what a Markov model is and a hidden Markov model, because this is like the building blocks we use. This is a probabilistic model which is used in language processing. And so, for instance, if you install Google Now and you talk to your cell phone, it's a HMM, it's a hidden Markov model combined with the neural network now. So it's really state-of-the-art, these methods. Then I give an example to really highlight why this model is useful. I will go to a text processing problem because we also process text data. And then I show some frequency distribution of functions call. That's basically the sequence I want to learn. Then I show some visualizations about these matrices and how we can sample from the model and make prediction in the future. So we all know what an LBUG is so far. So Lustre is, of course, a very large project with complex code base, and we're all humans who are making mistakes. So Lustre is like every other huge project critical to software bugs, and it's called Lustre. And I just make here, like, this is somewhere in the header data, if I'm not mistaken. That's just the code. And if you go to this wikilustre.org website, you can see node LBUG freezes the thread to allow capture the padding stack. The system reboot is needed to clear the thread. So it's basically like a bad guy which we want to analyze and to predict. Here is another example. It's just some code snippet from the NDT. And basically, you just check whether valid has this kind of values. And then you say, OK, it's some undefined value, so I throw an LBUG. This is like an example how LBUGs are thrown. And we actually faced so what we done, we running at GSI a huge Lustre cluster, like Walter said, we have around 9,000 disks and several OSS and so on. And so this work was basically motivated by one of my colleagues. He's our like logstash expert, and he came to me one time and he said, you know, Thomas, can we analyze log data? And I said, what do you mean by analyze? And he said, you know, I want to somehow extract knowledge. And I said, okay, define knowledge. What is the error function? What do you want to minimize? What do you want to do with this data? And so we had a nice chat about it, and then I said, okay, let's apply a hidden Markov model and try to analyze this sequential data, because log data, what we see, so each line, I will show that in the next slide, we have textual data in some sequential form. So this is just, again, an overview. We have actually a massive amount of data. So we had only for the year 2002, like 2.1 gigabyte of Lustre data. So this is filtered with Logstash, and he prepared the data. It's actually, well, it's a big data problem, but nowadays, also with GPU power, we face even much more sophisticated problems. So this is an example what kind of data Matteo, the colleague who is the Logstash expert, gave to me. So we exported then the CSV format, and so we have a timestamp, then the machine, then whether it's a Lustre or a Lustre error, then the C file, then the line number, and then the function call. And I said, let's first start with the function call. So for instance, here you see this server, bulk callback, and so on. And here is an LBUG. Actually, I want to highlight that this LBUG is already fixed. But we had it in our logging data, and it was for me a very good starting point because I had this data with LBUGs. You know, when you try to do it by yourself and say, I want to crash the system, you just cannot do it. Well, if you have a version where you know this LBUGs and you go for that, then of course you can do it. So this LBUG is already solved. But we actually faced this LBUG several times before we installed the patch. So when you just go back and say, okay, now let's look how we can apply a machine learning method for that. So I'm concentrating here on log data and on the function calls. And they have a sequential order. And here is some example. When I first draw it on a sheet of paper, the function call, and I said, okay, what happened? We have, for instance, the function call MDT open, MDT fseek, and so on. And then we can like emit a symbol or like emit a state. Was an LBUG hit or not? And when you see that, and you lecture for several years at the university machine learning class, you say, well, let's apply a hidden Markov model for that, because this is a very similar form. So what is a Markov model? What is a hidden Markov model? I love this beautiful weather example, and I will introduce a hidden Markov model and then the 3 problems, and then it looks like it's not related at all to any Lustre log data, but I make the connection via this text processing example and how we extract latent structure from this data. So what is a Markov model? Well, we have here is this classic weather example. We have 2 states, one rainy state, one sunny state, and I have a start state. And so I fully specified the model like with 2 parameters, the starting vector and the transition vector h, call it h for hidden. And then I said the probability that you can just imagine you toss a coin. The probability for rainy is 0.6 and for sunny 0.4. And then you go to rainy. And you stay in the state with probability 0.7, or you go to a different state in the next time series probability 0.3 to sunny. So this is like the full specification of the model. And when I will visualize the Lustre data, I will visualize these matrices. This is what we want to learn, these values from the data. So you give me the data, I run my algorithm, infer the value, and have these values in the matrix. I don't know whether I say that, but you know, another important thing is that basically we want to model the joint distribution of the sequence. This Q is like a random variable. It's just a mapping of some event space to some real valued number. And then we want to model the full joint sequence. But this is usually impossible. That's why we constrain the model to the first order Markov assumption, and I said the past only, the jumping in the next state based only on the last state. I forgot basically the whole history except the last state where I was. That's the first order Markov assumption, right? And there's a second order, and then I keep in mind the last 2 states, right? Then I have like a 3-dimensional matrix, and I have another dimension. That's what it is. So to summarize keep in mind, we have these matrices. Okay, I probably will skip that. For instance, you can ask a question like, given that the weather on day 1 is sunny, what is the probability for the next 3 days? So the weather will be, for instance, sunny, rainy, rainy. What's the probability for that? Well, you just start with a start vector, it's sunny, and then from sunny to go again into sunny state, then in the rainy state, and that's exactly what you have in the matrix. That's what can do with this kind of model. What is now hidden? What is the hidden Markov model? Why is it useful? Suppose we are locked in a room without any windows, and somebody is telling us that the following observation, and ask him to tell him what weather is outside. So I don't know this state, rainy and sunny. I only observe. This is like a random variable which you observe. That's why this node is gray. So I'm locked, and you tell me, well, I went walking and shopping and cleaning and so on. How was the weather? I don't have access to this. So I tell, well, it's highly likely that you went walking. It was not really rainy. So I predict, well, the corresponding like hidden state was sunny. Right? So this is the hidden part in the hidden Markov model. And this is like latent variables which somehow connect these observable variables. So what is the next parameter we have? We have an emission matrix. I toss the coin, go to rainy, and then I emit a state. Because the probability is pretty high to clean my apartment because it's rainy, 0.7. And that's exactly like this kind of entry in this matrix, right? Okay. Is that so far? You can, I mean, there are whole books. You can teach that for like a month. In Markov models, and when you show the algorithm to learn it and so on. I just want to make this intuition, right? We have these matrices, that's the whole point, and these are like histograms which represent exactly these entries in the matrices, and we will visualize them, right? Okay, there are like these 3 nice problems, calculate the probability of the observation and so on. Let me now introduce you this text processing example, how we can discover with this model interesting latent structure. And we want to discover latent structure in log files. Suppose I take the text, the text from the novel Flatland. So this is just the first chapter. I call our world flatland, not because, and so on. And then I do some processing and like convert all letters to lowercase letters and eliminate stop words and digits and so on. And so I have this huge, massive amount of sequential letters, right? So and now I specify I have 2 hidden states, and of course I have 26, the alphabet, lowercase, observable states. And if I run the hidden Markov model on that, and this is also now how I want to explain the visualization. So this is like the emission matrix, just in this form, multiplied times 100, so you can better read the values. I just run it, and then I use this chord diagram to visualize the matrix. So this length of the arc corresponds to the value of H1. So the bigger the value, the larger the arc. And what you see, if you just run the model, it automatically discovers that this is text and based on consonant and vowels. He just said there's a high probability to go from this H1, from this H2 to an O, I, E, A, and so on. And if you go read, and if you read any papers on language processing, and you would tag text the letters with C and with V for consonant and vowels, there is this latent hidden distribution which the model automatically recovers. I haven't told him anything. And I said, look, I give you the sequential data. There's a learning algorithm to estimate these values in this matrix. And then I visualized it. And he told me, yes, the latent structure is I discover vowels and consonant. And I said, wow, cool is that? Why not apply that to logging data? So this is the motivation behind the work, and this is what I want to now. So this visualization makes sense so far, this code. It's actually, there's an interesting R package, which does that all for you. So here's just first results. If you just take our logging data from, I just extract only the machine name LXMDS11, that's our MDT server, on the January of 2013. So I looked at how many entries were there in there, and then I extract the function calls, and then I just plotted the distribution. So you see already there's some regularity of function calls which show up very frequently. So when, for instance, some OSS, or actually when the MDT has problem, the OSS started like to reconnect again, and then this logging file is like growing, and then basically the counter is going up. So this is called the n-gram model. I just have the frequency vector. I just leave it there. If you're interested, the slides will be then published. So, okay, now comes another interesting thing. What happens if we visualize the Markov model not hidden? So again, you give me the logging data for 1 month for a certain machine for LXMDS11. I extract the sequence of function calls. I train the model not hidden. So I don't have the emission matrix. I only have the transition matrix. Right? And then I visualize this with this chord diagram. And wherever you see this arc and you see like a line connecting, then it means this system call, logical object volume find pool, was a repetition. This happened several times. And when the system call was LOV find pool, and then the next one was target handle reconnect, then you see this kind of line. Right? So you see there's a lot of repetition, which makes sense because this was MDT data. But this is only like the Markov model, not the hidden. So I did this visualization, and then you see basically you have these 3 big classes where you have this repetition on system calls. Well, you can also go now in the log data and see that by your eyes. That's not a big deal. It's just a way to visualize this. And that's why we go a step further and apply this hidden Markov model to recover this latent structure, this vowel consonants. Okay, I have the 30 minutes, right? 10 minutes left. 5 minutes. 10. Well, okay, I will skip that and go immediately now to the hidden Markov model. So if you train, again, I have to be here concrete what kind of data I use. I used the whole data from year 2012 and extracted, because we had only LBUGs on the MDT in January, in March, and in August. And from these 3 months, I extracted the lines of the CSV data and trained, so I had in total 38 unique function calls, like the emitting states, and I trained the model with 2 latent states. And so, as we have this example with all vowels and consonants, you can see that these 2 latent states basically match to this mainly target handle reconnect, and that we have this logical object volume find pool. And you see also that they are somehow related. So these 2 hidden Markov model does not give us really much more information than the Markov model. But what happens if I increase the number of latent states? So the number of hidden states. Suppose I use the text data and say, look, what happens if I train that with 10 hidden states? I look for vowels and consonants. What kind of regularities are else in this data? And that's what it's showing basically the next graph. So interesting is like the 4 hidden states. Now it starts to separate. So we have like this 4 hidden states, and you see there is a close relation to like target send reply and MDS close. They belong to the same latent class. I have to admit that I'm not the core expert in really interpreting now, because when you see this language model, then you know from school and all this grammar what that means. But if you now go deeper in the data and you look how the function call calling each other, they're like this latent class where they belong together. But it has not necessarily be part of the function call immediately. It can be like linked through a latent state. So that's a beautiful other probabilistic model called latent delay allocation, which is I think Google now using. So suppose you want to classify news data, textual data, and it's about politics. And there is like also a football game in it, because President Obama visited a football game, but his name was not necessarily like mentioned in this text. Then you can still put him in this latent class like politics, although he was linked via football to this class. And that's basically what this thing is also telling us. So I will release the code on my Bitbucket account. You can play around, discover other relation. That was basically this analysis part. Now, how can we sample from the model? I forgot here something to tell you. I go back to this model. Of course, what I also can do, once I learned these matrices, I can sample. I can generate artificial data. I can generate my own text now. How is that possible? Well, I have the full specify model, and I just sample from it. So I toss this coin. I'm ending up in, let's say, state sunny, and then I have, if you're a statistician or a computer scientist, you would say that's a multinomial distribution. So any kind of like MATLAB or R, you can sample from a multinomial distribution. Is I specify exactly this vector, and then I generate this emitting state. And I do that several times. And if I sample from the model, I generate like my own artificial function call sequences, right? And this is exactly what I did here. So this is one example function call sequence the model generated with 2 hidden states. And if you just compare it, I unfortunately have no comparison where I take the next month and really make a match and say, look, I exactly predicted the right emitting state. This is what you do in genetic analysis when you use this model. And then you see how many hits you have and how many losses. And then you can tell something about the accuracy. Unfortunately, when I use the data, I saw I have much more LBUGs in the data, but I had only like 7, 8 LBUGs of this type. The LBUG occurs several times, but it was exactly the same LBUG before the machine halt. So I cannot say, okay, I have 10 LBUGs in it, because it was technically 1 LBUG. So Lustre is pretty good, you know. It's not this big problem with these LBUGs, because you don't have so much of them. But what you can do, you can ask now, I train this model and ask, what is the expected number of LBUGs within the next t time step given this 2 hidden state model? And I just plot this graph. So as I'm sample from the model, let's say around 2,000 time steps. These are like 2,000 lines in my Lustre logs. Then there's on average will be 5 LBUGs. But like I said, this model is highly underrepresented with these LBUGs. So one really has to be careful. If you have more data, we can talk, and I would love to crunch more data with more LBUGs. But this is basically what the model is saying. Let me just summarize what we did here. It was like a first approach, and I think you see this field of applying data mining, machine learning methods to analyze behavior of file system, log data, whatever, is an interesting problem. And we produce massive amount of data, but the data is there. It's just there, and it's barely analyzed. So I use this opportunity to like introduce and motivate this interesting problem to learn more from the Lustre logs and analyze the behavior. So we're able to visualize and analyze the problem. Like I said, the most interesting is to recover the latent structure. I will also put all these images on this website, and then you can go through it, and probably you see different things in. Of course, it still needs human interpretation. Like I said, when I also train this LDA model, I put these things into classes, and then I have to label this latent class and say it's about politics. I cannot infer that. Like I said, it took me like 3 months to get this implementation in C. When you run this model and you calculate probabilities, what happens if you multiply, let's say, a sequence of 10,000 function calls, and each is a value smaller than 1, much smaller than 1? Well, you have numerical instability. That's why I usually take the logarithm and add this up, because the multiplication, if you take the logarithm, it's a summation. So you need all these tricks, you know, to do that. And I also have R scripts for generate that. This will be available. And many thanks to Matteo for providing this data and this endless discussion. I mean, I think he's now also into this machine learning. He's attending on Coursera like Andrew Eng's. He's a Stanford professor now at Baidu Research. He's very famous in this field, online classes. So I also can recommend if you just have free time and you're very interested in this problem, it's really an amazing field. Okay, thank you.
How do you see connection between your investigation and development process? For example, do you see any way how to create Jira ticket from your prediction?
That's an interesting problem. My grandmother always asked me when I work at the university what I'm doing actually. Is that useful? and you know, there are moments in your life where you adopt that, but the problem is currently that when I saw the diagrams, I have this lack of knowledge to really have a deep interpretation what that means in terms of like the function call flow in the process when Lustre is running. You know, but I am very confident because these methods are not new. Hidden Markov Model are there since they were like used since 85, 86. And this is like the starting model, and they're much more advanced model for text processing, which we can borrow the methods and really discover something. But I have to agree in some point, of course, when you are working on that, you always have to ask yourself, is that useful? Yeah.
Have you tried using other statistical machine learning approach like PCA analysis? Because I think Markov model is a stateless model, and this analysis where you are depending one function call to another function call, your LBUG will depend on that. So that will require some knowledge of state. And probably this PCA kind of approach where the principal component analysis and other statistical machine learning approach could be better. I don't know. I haven't explored this. I'm just thinking.
You know, with PCI, you basically map high-dimensional data into low-dimensional data by minimizing the reconstruction error. And what you basically have, you do that like in JPEG images, but I have sequential data, and I have different lengths. So I have actually not like fixed value 10-dimensional data, which I want to map to a 2-dimensional space via linear mapping and then discover the interesting problem. But I agree, probably I can say, I did some work with one of my students in Munich, and we used a much more sophisticated model to predict like malicious behavior of processes in Linux.
Okay.
And we incorporate even more data. Now I use only function calls, and they are like the lines of codes, which also helps us like to guide this model. This is still there, and one needs to exploit that. So I see definitely a potential to apply different kind of methods. By PCA, I'm not sure. You know, for me, PCA is that I want to visualize high-dimensional data in some low-dimensional space and find interesting structures.
So the way I look at high-dimensional data, for each line of the Lustre log, you must be extracting some n numbers of items. Functional call, number of types the function is called, some, I don't know, timestamp. So if you collect n features from same line, so you can do PCA to reduce those n features to, you know, some 3 features. So something like that, I can look at it.
If there is a linear relation, otherwise I use like kernel PCA or something, you know, I have to exploit this linear mapping into this low-dimensional space. Yeah, but this could be also an interesting way. I haven't looked at that, yeah.
So, and currently, what are the features you take it from the single line of the log?
Only the function call.
Only the function call.
Like I said, it was like the first building block I used, which come in my mind. And there's a huge potential to exploit and use much more features, because usually the more features you use, when they are not redundant, you can kick them out, then the more powerful the result finally is. Yeah, that's true.
Thank you. And do we have this implementation available for us, this your HMM implementation in C?